Hey, I'm David, and this is Lab 4, covering springs and oscillations. Okay, so for the purpose of the lab, we wanted to study the motion of a mass that's attached to a spring that's swinging in an oscillating motion. And then we put that into the tracker and observed the data using the center of mass. And then we compared that observed data to a computational model in order to determine if the energy principle was obeyed within the system. Okay, so the fundamental principles we're focusing on in this lab are Newton's second law and the energy principle. And here are the models for those. So Newton's second law, basically what this is saying is that the net force is equal to the change of momentum related to time. And for our energy principle, there are two formulas. Basically, our delta E for the system ends up equaling zero, because these go to zero when our system is like the entire Earth. We don't have any surrounding forces or anything doing work from the surroundings. Sorry. So we end up with this formula. And here's the video that we used. Uh, Basically, as you can see, the spring is swinging around in an oscillating motion. Okay, so for our code, our initial conditions, we just had the ball mass, its position, its velocity, the force due to gravity, spring constant, the relaxed length of the spring, and then these will calculate like the length of the spring currently, and these will compute the system's energies. And then here we have our loop, which is going to calculate the gravitational force and the spring force and use those to calculate the net force, velocity and position update formulas, update the spring, and then calculate our energy changes. Okay. Here are graphs. The blue line is the model and the red line is the experiment. As you can see in the X versus time graph, they're pretty close together, basically the entire time. And then the Y graph, there's a little bit more discrepancy, but they are moving in like relatively the same manner. Okay, so our potential error, there could have been tracking errors, just missing like the exact center of mass with the tracker or things of that nature. And then outside forces that we didn't account for, like we didn't account for air resistance. So those would change our observed data a little bit, or our computational, I guess. What does it mean? For the model, is the energy principle satisfied? Yes, it was, because our change in total energy remained at zero for the entire time, which you can see here, it's the orange line. And then for the what does it mean, we wanted to find two separate estimates. The first one being the oscillation period in the X direction, and the second one being the oscillation period in the Y direction. And so for the X, we got 1.71, and for the Y, we got 1.52 seconds. Thank you.